Hello, this is a British Psychological Society audio interview. I'm Wendy Barnaby, and I'm joined by John Aggleton, Professor of Cognitive Neuroscience at Cardiff University. And John, we're going to be talking about your research into different sorts of memory.
My work originally started with looking at amnesia in humans. Amnesia is both a very tragic event, but it's also very informative to psychologists. And it's very informative because people can have a very selective loss of memory, but other cognitive abilities are left remarkably spared. So it's telling us that if there's a brain injury that's causing the amnesia, that structure is critical for aspects of memory, but is not critical for a wide variety of other cognitive abilities. So it immediately gives us a set of targets to look at, telling us that these structures are potentially incredibly important in memory. Anybody who's read anything about amnesia, they've come across HM, I'm sure the most famous neuropsychological case there is, will know that the hippocampus is seemingly vital for learning new information. HM was a gentleman with severe epilepsy. It couldn't be treated by drugs, and in 1953 the surgeon Scoville decided to remove tissue on both sides of the brain involving the hippocampus. And on recovery from the surgery, it was evident that he had an absolutely devastating amnesia, both an inability to learn new information and in fact also amnesia for past information. And he never really recovered. But at the same time, his IQ, as measured by classic IQ tests, was effectively unaltered. So he had no problem at all in maintaining a conversation with people, understanding what people were talking about, but he couldn't update his memory at all. And he was kind of the landmark model on which the understanding of amnesia has built on. So there's a structure called the hippocampus, which truly does seem to be involved not just in initial processing but initial coding and storage. And we know a lot about plasticity, how neurons within the hippocampus change following experience. But we also know, and this is very much my kind of work, that in coordination with other brain structures, so structures in a part of the brain called the thalamus and certain other cortical structures, that coordination is required, but we don't suppose that those memories are laid down in those other areas, but they're vital for the process.
So the take-home message is really that there are loads more brain structures. There's a sort of a network that is involved in memory rather than simply specific parts of the brain, which is what people have thought of.
I think people have long been aware that there is a network of structures, and people for a long time appreciated, for example, the importance of certain cortical areas, such as cortex in the temporal lobe, and also prefrontal cortex in coordinating what's going on. But the problem has been that research has classically focused on a very limited number of sites. And although we have found extraordinary information, for example, about the hippocampus, the danger has been that that has really overshadowed and rather given a distorted view of how these other structures contribute and what their roles are and their importance. And without that more comprehensive view of the brain, we actually do end up with a distorted view of what's going on. And that's not just inaccurate, but it also poses problems. So, for example, if we want to understand the processes that lead to cognitive loss in things like dementia, we need to know the full array of structures that are being affected and malfunctioning in the progression of this disease. And it turns out that, yes, the hippocampus is a structure that's affected quite early on, typically in Alzheimer's disease, for example. But so are these other brain structures in the thalamus and certain cortical areas that we've tended to overlook. And in fact, if you use functional brain imaging, you can show that there is a cortical structure, it's called the retrospecial cortex, which shows the very first metabolic changes, or activity changes in the progression of Alzheimer's disease, but it's hardly been a target for people looking at the origin, the course, and potential treatment of this disorder. And it just highlights this fact that we have to adopt a broader image, and that broader image, of course, isn't just grabbing areas in the brain, it's also understanding how they're interconnected. We have to know about the structure and the anatomy to understand how they work together, and also what happens when they start to fail.
Would it be possible to take an fMRI scan of the retrospecial part of the brain to diagnose when somebody was about to get Alzheimer's?
That's a very exciting question. There's a condition that is more common than Alzheimer's disease called mild cognitive impairment. So this is typically what happens to some elderly people who show a more exaggerated loss, in particular, of memory. Some of those people, over time, go on to develop Alzheimer's disease. Some of them don't. But if you look in people with mild cognitive impairment and you look at brain activity at different sites, the site that is found to be abnormal in these patients is the retrospinal cortex. So that change is occurring before any real diagnosis of Alzheimer's disease. That then takes us to the very interesting question of, firstly, can you use this as a marker? Well, the problem is, of course, because actually you'll find this in people with mild cognitive impairment who don't always go on to Alzheimer's disease, it will not be a perfect marker. But it may well be that people are showing subclinical symptoms for years, for decades maybe. And that then raises the question, well, where should we be looking? Where should we be looking for changes in brains of people who clearly at the moment don't have Alzheimer's disease? They don't have mild cognitive impairment. But, for example, because of genetic information, we know they might be at higher risk than others. Well, this bit of cortex, called the retrospinal cortex, would be a perfect candidate to look for just those changes. And people are starting to do just that kind of research.
So your research is really giving clinicians pointers about where they should look.
It is indeed. Just to carry on with this bit of cortex called retrospinal cortex, this is an interesting case in point because in the human brain it's buried deep in the midline. It's a very difficult part of the brain to access. You have a few number of patients who've had stroke damage there, who show memory problems, but again, these aren't very common and they're very difficult to interpret because of the position of the structure. In contrast, the retrospinal cortex in an animal like a rodent is relatively large and much more amenable to study. And so we can find out a lot more about what the retrospinal cortex is doing in, say, a rodent. It has exactly the same structure, the same cell types in rodents as it does in the primate brain, and it has the same main connection. So again, it makes it a very interesting and exciting target to study.
Do you think that that's the main pointer to clinical application that your research is coming up with so far?
It's clearly one of them, which is this looking at other targets. And then that becomes very important if, for example, you're looking at disease models. So if you're looking at a genetic model of a disease, you want to know that you're looking in the right brain areas to look for dysfunction. Otherwise, how can you interpret or test the validity of the model? But I have to make clear that inevitably, much of what I'm interested in and much of what I'm doing is just trying to understand the brain as it is. So if all my concerns were about trying to understand dementia, I'd be doing research in a different way. My genuine and honest priority is trying to get to grips with this spectacularly beautiful, stunningly complicated, wonderful organ that we have. And that's really what, drives me and gets me very, very excited.
John, thank you very much.
It was a pleasure. Thank you.